All right, so welcome to that third and final video on aim constraint, where we are actually going to pretty much build the same setup we've built inside of Maya in the previous video, but this time inside of Bifrost. So I'm going to just kind of piggyback on that scene we've built in Maya. I'm going to be using the same transform with those three like curves shapes with the line width set to 10, just as a visual representation of our transform. If you haven't seen the first, like the Maya video in the beginning, I explained why I tend to use that, because it's just an accurate representation of the matrix we are going to build, as opposed to Maya's transform gizmo or the local rotation axis. I go a bit more in depth in the Maya video. You should start to watch this one if you want to understand why I'm doing that. Yeah, so in the previous video, we've built this node graph, which we are simply going to delete right now. That completely broke the transform gizmo, so I'm going to reset that to an identity matrix. So that's going to be 1, 0, 0, 0, and this row will be 0, 1, 0, 0, finally 0, 0, 1, which is already right, 0, and then 0, 0, 0, and a 1 over here. Cool, so we've got our points A and B. I'm just going to hide the shapes and place B kind of over here. A is fine. I mean, all these points are fine where they are. And yeah, so let's actually build a Bifrost node. So I'm going to go into display and then Bifrost graph editor. And I'm going to create a new graph. If you're used to Bifrost, you probably know Bifrost creates a DAG node by default, but we would prefer to have a DG node, which is simply going to be a node that only exists in our DG, but doesn't show up in the outliner pretty much, or isn't a transform. So if I go back to the Bifrost graph editor and go in display, convert graph, convert to DG node. Now that node disappeared from here, but it still is right here. I'll just call that a name constraint. And the first thing that I want to do is actually expose some attributes right on that node, because that node is really empty right now. It doesn't have any inputs or outputs. I've never really found a good way to create attributes in Bifrost. So the way I tend to do it is just create a multiply node, or whatever node really, and just connect something in it. And then I'm going to rename that port to A, and then set its port type, because right now it's just a float. I want that to be a vector 3. And yep, that's pretty much it. And then the way I'm going to create the other attributes is just create one on the output and then connect that 3 times to the input, and then rename, call that B, and then call that C. You could give better names, like this could be the up vector object or something, and then this could be the origin and then the target. I'm going to break that connection and make that the output matrix, and then change the port type of it to be a matrix. That's going to be a 4x4 matrix, which is the default, and a 32-bit floating point matrix is more than fine. Cool, so we've got that data. I have no idea why that's set up like that, but I wanted to go in the node editor. So yeah, we have our inputs, we have our output. Let's actually connect the translate of each of these nodes right here and connect the output matrix. This is going to break pretty much instantly, right? Our transform disappeared. This is simply because the matrix is filled out with zeros instead of being an identity matrix. So our object is all scaled up to nothing in the center of the world. So let's create a value node, which is a node that can be of any type and has an input that we can set manually. over here, and an output that we can connect out. So we are going to change the type of the node to, again, a 4x4 matrix of 32-bit floats. And now we can actually end up connecting things inside of that node. And we can also set that matrix to be an identity matrix by using ones in the diagonal just to start with. And if I connect that up, now our object is back to what it should be. Cool. So the first thing that we'll do is place our transform to be positioned on the point A. The way we would do that is to connect that like so. But you notice that we again broke our setup. This is because our point A is a vector 3. You can see at the bottom. So if you look at the bottom of the screen, if I hover over A, you can see it's a float 3 attribute, where this is a float 4 attribute. And then the conversion, in this case, or like in any case, a float 3 to float 4 is just going to add a 0 as the last value in the vector, which is not what we want because the identity matrix ends with a 1 for the translation. So we can use a vector 3 to vector 4 and then simply feed that in right here and use a value of 1 for the W. And then we can use A right here, and now our object is placed on A. We actually cannot see the values, which is a bit unfortunate. But yeah, you should know that this is all connected up properly. So yeah, that's pretty much it. I'm not going to actually need a vector 3 to 4 node for all the other vectors, I'm pretty sure, because again, that conversion will fill zeros out properly. One thing I forgot to mention is, as opposed to Maya, the matrices in Bifrost are column major. So that means that instead of storing, like, let's say the X vector in the first row, like so, it's actually stored in the first column. So this is our X vector, this is our Y vector, this is our Z vector, and this is our translation, which is why these are great at right now, because these are the only ones that we have connected to the 4x4 matrix node. Cool. So yeah, let's actually jump into it and solve the vectors. So let's just do X first. So that's the normalized vector, the one with the little hat, that goes from A, sorry, and points towards B. So let's create a subtract node. We are going to subtract B from A, not A from B, sorry, so B first and then A. And this is our X vector. And if we plug that in here, we have our X vector that stretches that all the way towards B. Like in Maya, we want to normalize it. Bifrost has a dedicated normalized node that we can just feed into there. And then we can connect that to our X. The nice thing about that is we can actually connect an actual vector directly instead of having to split all the data into the X, Y, Z, and W components. So yeah, we have our X vector, sorry, that doesn't stretch, sorry, and points towards B. So this is the first step done. Now let's just build our up vector. Again, I highly recommend that you actually watch the first video of the playlist, which goes over the math of the M constraint, because right now I'm just using that to just build the node graph in Bifrost. So let's build the up vector, which is this time doesn't have to be normalized. It can be normalized, but it doesn't have to. It's just a vector that goes from A to C. So the way you build that is another subtract node, and we want the vector that goes from A to C, so we do C minus A, and this is simply our up vector. And let's just call that up vec like so. I'm going to pull that away and keep that node out like so, or actually I might keep it down here so that it doesn't really overlap with the rest. So we have our vector, we have our x normalized, vec normalized, and we want to, from that up vector, we want to solve the z vector, which is simply the normal to the plane defined by x and u. So like it's written here, we do the cross product between x and the u vector. So Bifrost has, again, a dedicated cross product node. We feed in x first and then the up vector. We can call that z vec, and we can plug it into here. You'll notice this isn't normalized because the output of a cross product simply isn't necessarily normalized. It, I think, depends on the length of the vectors we feed in. So if both of the vectors as input were normalized, we might be getting normalized vectors as the output, just in case. I might be wrong on what I just said, by the way. But just in case, I tend to normalize everything that I know will need to be normalized. So we can pop a new normalized node and connect that up like so. So that's z vec normalized. And oops. Okay, so we have x, we have z, we have our like a vector that kind of exists in the middle. And then finally, we can compute y. Y is going to be the normal to the plane defined by x and z. And the way we compute it is going to be z cross x and not x cross z. And I'm going to show why in a second. So cross product, we'll do, let's actually do it wrong and connect x first and z second and connect that out. So y went straight down because the order of the cross product really matters, and one configuration will give you one vector and the other configuration will simply give you the opposite vector. In this case, we want y pointing up, and I guess this y vector is normalized because both of the inputs are normalized. I want to actually check that. So length, I'm going to get the length of that vector and let's say just output that to our node. Now that this is connected, I think we can just add a watch point and see that if we move these around, yeah, we seem to still be getting a normalized output in all cases. Okay, so technically you might not need to normalize the y vector. I am still going to just do it just in case because it doesn't really hurt to just have one more normalization. The math behind normalizing shouldn't really be too intensive, computationally intensive. That was a mouthful. But yeah, we have all our vectors, x, y, which is over here. I'm going to rename to y vec normalized. And then the z vector, which is, again, normalized. Yeah, we have the exact same setup as we did in Maya now, except we just have one single node here. We can delete that length attribute, which shouldn't really need to show up. We've got one clean DG node inside of Maya and well-functioning aim constraint. Now, Bifrost, as nice as it is, like the graph is pretty nice, it's really nice to just have one clean aim constraint node inside of Maya. Unfortunately, I haven't tested this in a bit, but I I'm pretty sure that Bifrost is still fairly slow for rigging. So I do not think it is a great option for rigging, but it is a really nice tool to play around with. And we'll see, especially in the later videos, that it can help us build things that can be really useful while you are rigging, but that don't necessarily need to be in the final rig. So yeah, basically tools that help you as a rigger, and that you won't need in the final rig. Yeah, so that's pretty much it. That's how I tend to use Bifrost. Just using it to write custom nodes without actually having to write a custom node. So yeah, that's pretty much it. I will see you in the next video, which I'm probably going to cover IK solvers in. So that's another pretty interesting topic to know about. Cool. I will see you there. Bye.